Okay, the story so far, we reviewed momentum and impulse, and we also talked about how momentum is conserved in a one-dimensional collision. And I'm not going to go through everything again, but here is our collision. The objects are approaching each other. They apply forces to each other during the collision. By Newton's third law, those forces must be equal and opposite, and they happen for the same amount of time. Both of these forces are applied for the same amount of time. The impulse momentum theorem says that force times time gives me the change in momentum for each object. They're equal and opposite, so I can rearrange this to say the change in momentum of object 1 plus object 2 must equal 0. Therefore, there's no net change in momentum for my overall system, so P initial equals P final. Momentum is conserved in a collision. And this is true for all collisions. All collisions in the universe, if you're considering them to be an isolated system, the momentum within that system is always conserved. And the individual objects may change their momentum, but the total momentum doesn't change. Okay, so now we're going to talk about an elastic collision. Now, an elastic collision is one that's about as bouncy as you can possibly get. And when I get back to class, I'll go ahead and do some demonstrations on the difference between, an elastic collision and an inelastic collision. But let's talk about elastic collisions. Now, in an elastic collision, we have two equalities. We have the initial momentum of my system is equal to the final momentum of my system. This is where you start, and this is always true. Always true for all collisions. But in an elastic collision, something else is conserved as well, and that is kinetic energy. The initial kinetic energy is equal to the final kinetic energy. Now what that means is that during the course of bouncing, that we don't transfer any kinetic energy into heating the material. Or if you had an elastic collision, it would be totally silent. It wouldn't give off any sound. The two objects would come together and bounce off each other and go apart, and they will not have lost any kinetic energy. These actually happen quite a bit at the microscopic scale, or the scale of the atom, or sometimes when galaxies collide or interact gravitationally, there's really no loss of kinetic energy. But for most collisions in the real world, almost all collisions are actually inelastic collisions, but some come so close to being elastic collisions that we can model them that way. And so let's talk about this. Now, if we have two objects colliding elastically, we can take these two equations and expand them, and we can say m1 v1 initial plus m2 v2 initial is equal to m1 v1 final plus m2 v2 final. We can also write the conservation of kinetic energy during an elastic collision. 1/2 m1 v1 initial squared plus 1/2 m2 v2 initial squared is equal, I don't need the vector hat on there, let me fix that. When you square a vector, what you're really doing is you're doing the dot product of the vector with itself, and so it's a scalar. 1/2 m1 v1 final squared plus 1/2 m2 v2 final squared. So these are the equations that we can use to solve problems involving elastic collisions. Now, when you're doing a problem, given, find, and solve, what if you're given the masses and you're given the initial velocities, and what you want to know is what are the final velocities? Well, if you're asking what are the final velocities, you're asking for what is this velocity and what is this velocity here. Well, those are two unknowns. So what you need are two equations. Well, here we have two equations: the momentum equation and the kinetic energy equation. Well, let me tell you something. If you try to solve these simultaneously, like two equations, two unknowns, it's messy. I mean, it is an algebraic nightmare. And I used to try to derive it in front of class every time. And you know what? I never got it right. I always made a mistake somewhere and wasted a lot of time. So you know what I'm going to do? I'm going to leave it to you. Solve these two equations simultaneously for V1 final. Solve them simultaneously for V2 final. And what you get are equations that are listed in the book on page 262. And we're talking about equations 920, 921, and 922. 922 works if one of them has an initial velocity that's 0, and 923. Now you can look these up in your book. Okay, this is Survey 6th edition, Physics for Scientists and Engineers. I'll just write 920 down for you. V1 final is equal to M1 minus M2 over M1 plus M2 times V1 initial plus 2M2 over M1 plus M2 times V2 initial. So that's equation 920. So this gives you V1 final in terms of the masses and the initial velocities. Now how do you get from here to this? It's crazy, but you do it. Okay, V2 final. Actually, I have been known to give extra credit to students who work out all the math. So if you want to solve these simultaneously and get this, bring it to me, and I might throw you a little extra credit. So V2 final is equal to 2 M1 over M1 plus M2 times V1 initial plus M2 minus M1 over M1 plus M2 times V2 initial. And that, look, these are pretty much just crisscrossed right here. It's just a variable name change. What you call 1 and 2, it's pretty arbitrary. But anyway, these are the equations. This is 920 and 921. These two are if you just assume that the second object has a 0 initial velocity, so you just eliminate these terms, and this is what you're left with. But these are the equations you use to solve elastic collisions. I've never seen an elastic collision problem on the AP test where you would have to memorize these. What you mainly have to understand for elastic collisions is that kinetic energy is not lost in the problem. Okay, so let's go on to inelastic collisions. In an inelastic collision, and most collisions are inelastic, well, we have momentum is conserved. The initial momentum equals the final momentum. That's always true for all collisions. But when you have, in a real collision, like I'm going to collide my hands here, so let me zoom out so you can see it. Here is an inelastic collision. Okay, ready? Boom. Oh, you know what? This camera is so slow. Let's do it in super slow motion. Here it goes. Bam! Okay, now when it did that, equal and opposite forces are applied for equal times, so they have equal and opposite impulses, which means there's no net change in momentum of your overall system. However, sound was given off. The surface of my hands kind of hurt. It heated up the environment. It transferred some of the energy from kinetic energy into the internal energy of the material. In other words, we lost kinetic energy. The initial kinetic energy is greater than the final kinetic energy. Okay, so this is what defines a elastic collision. Now let's talk about what a perfectly inelastic collision is. Turns out that a perfectly inelastic collision, well, let me write it. A perfectly inelastic collision. In a perfectly inelastic collision, we're really losing the maximum amount of kinetic energy. But what happens, and let's just draw a little picture of a collision here. And whenever you do these problems, it's a good idea to draw the before the collision and the after collision picture. So here's a before collision. Here's my little car. And here's a, like a great big old SUV or something. The new SUV, it's coming out, Ford is coming out with a new SUV. It's called the new Ford Compensator. Okay, so anyway, this is a great big car, and they're going to collide. So let's say this one is at rest, and this one is moving. Now they're going to collide. Boom, they collide. Well, when they so this is the before. And you know what? We'll go ahead and give this a little bit of velocity, so that we'll call this object 1 and this is object 2. So that before the collision, we can say, hey, look, m1 v1 initial plus m2 v2 initial is equal to, well, in a perfectly inelastic collision, this is what you're going to have. So let's draw my Lincoln, my new Ford Compensator right here. And here's my little Toyota Prius that I just crashed into the, okay, here, that's what's left of it. Here's my, I should have worn my seatbelts. Okay, but in any case, what makes this perfectly inelastic is that these two objects are stuck together. Stuck together after the collision. That's what makes this perfectly inelastic. Now what does that mean? That means that they are going to move off with the same velocity. The final velocity of the small car and of the big car are going to be the same final velocity. So in other words, v1 final is equal to v2 final. Those two velocities are the same. Well, what does that mean? That means that I'm just going to say, hey, this is v final. They're the same. So what happens is that this becomes one big massive object after the collision. And so what I'm going to do is I'm going to say m1 plus m2 is the total mass of my object now after the collision times v final. And what makes this a perfectly inelastic collision is that these two objects are combined into one and they move together with the same final velocity. So now what I'd like you to do is to work the example problems together. Do at least a couple of the example problems before you go on to do the problemathon for other things, okay? And good luck with all this, and I will see you on Monday. Bye.